This is the 20-second example video on our course on abstract algebra. And if you recall, the lecture video was about polynomial rings. And so let's start with some fairly simple examples. Let's expand the following products in the appropriate polynomial ring. So let's look at x squared minus 3x plus 1 times 2x squared plus 5x minus 1 in Q adjoin x. So that's the polynomial ring where the coefficients are seen as rational numbers. So this expansion would be essentially exactly the same as what you might do in a calculus type class. Okay, so we just have to make sure we distribute everything from the first term to the second term. So let's maybe look at the x squared multiplying first. So x squared onto 2x squared will be 3x to the fourth. X squared onto 5x will be 5x cubed. X squared onto negative 1 will be negative x squared. So that's a third of our portion, and then we have to do the negative 3x onto each of these. So this first will give us negative 6x cubed, and then we'll have negative 15x squared, and then plus 3x. And then we finally have 1 multiplied onto all of those. So let's see, that'll give us plus 2x squared, and then plus 5x, and then minus 1. And now we have to push all of these together. So let's see, we only have a single x to the fourth term, that's 3x to the fourth. And then we have 2 x cubed terms. Those will combine together to be minus x cubed. And then we've got, let's see, 1, 2, 3 x squared terms. Those will combine together to be, let's see, it'll be negative 14x squared. And then we have 2x terms. That will give us an 8x. And then a single constant term, that'll give us minus 1. So in the end, that's our product. It's that quartic polynomial. Okay, nice. And now let's do the following product inside of z5 adjoin x. This is going to be exactly the same game. So let's rip through it a little faster. So we have x squared times 3x squared, that'll be 3x to the fourth. Then let's see, plus x cubed plus 2x squared. Then let's see, plus 4 times 3 is 12, but that is 2 inside of z5. Then we have 4 times x. That'll give us 4x squared. And then 4 times 2 is 8, but that is 3 inside of z5. Okay, then 3 times 3 is 9, but 9 is 4 inside of z5, so we have 4x squared. 3 times x, that'll be 3x, and then plus 1, because 3 times 2 is 6, but that's 1 inside of z5. Now we've got to combine like terms, so we've got 3x to the fourth, and then we have this x cubed term and this x cubed term. Those will add to 3x cubed, and then let's see, we've got an x squared term, another x squared term, and another x squared term. So 2 plus 4 is 10, but 10 is 0 inside of z5, so we don't need an x squared term. And then for our x term, we have 3 plus 3, which is 6, but 6 is 1 inside of z5, so that's plus x, and then plus 1. So there we have it. Okay, so for our next problem, let's find all the zeros of the following quartic polynomial in z3 adjoin x. So inside of maybe Q adjoin x, you know, the rational field with polynomials, there's a trick to do this kind of thing called the rational root theorem. But inside of finite fields, maybe our best trick is just exhaustion. In other words, we'll try all elements of z3 and see which ones give us 0. So let's start by maybe giving this a name. Let's call this f of x just for ease of notation. And let's look at, well, all of the numbers inside of z3. Luckily, there are only 3. So let's look at x equals 0. But if we evaluate this at 0, we get 1, which is not 0. So that means that x equals 0 is not a 0. Now let's look at the next one. Let's look at x equals 1, but then we need to calculate f of 1, but that'll be 1 plus 1, and then plus 2 plus 1. So let's see, 1 plus 1 plus 2 is 4, plus 1 is 5, but 5 is 2. That's not equal to 0 inside of Z3. So now let's look at x equals 2. So let's see, f of 2. So let's see, 2 to the 4th is 16, but 16 is 1 inside of Z3, so that gives us 1, plus 2 cubed is equal to 8, but inside of Z3, 8 is equal to 2, so we have 1 plus 2, plus 2 squared is 4, so that's 1, so that'll be plus another 2, because we have a coefficient of 2, plus 1. But let's see, 1 plus 2 plus 2 plus 1 is 6, but that is equal to 0. So that means that x equals 2 is a 0. But now since x equals 2 is a root, that means we should be able to factor it out of f of x. So in other words, from the video, we know we should be able to write f of x as x minus 2 times g of x. But let's maybe help ourselves out a little bit. We know x minus 2 is the same as x plus 1 inside of Z3, because negative 2 is the same thing as positive 1. So that means we could really factor this as x plus 1 times g of x. And now let's do that factorization just to see what we get here. And we'll do this using standard strategies of long division of polynomials that you learned way back in the day. So factoring x plus 1 from, let's see, we have x to the 4th plus x cubed plus 2x squared plus 1. Okay, so in order to achieve this x to the 4th, we need an x cubed here. That gives us an x to the 4th plus x cubed. And then we group and subtract, but we notice that everything cancels. Now let's bring this 2x squared plus 1 down. I'm going to leave a little gap there for my linear term. In order to achieve this 2x cubed, we need a 2. So let's add plus 2x. So multiplying that will give us a 2x squared and then plus 2x. And then grouping and subtracting will give us a negative 2x plus 1. Oh, but let's recall that negative 2 is the same thing as positive 1. So we can replace that negative 2 with a positive 1, which gives us a clear need to put a plus 1 right there. And then that'll give us an x plus 1 here, giving us a remainder of 0. So that means our factorization is actually like this. We have f of x equals, let's see, x plus 1 times x cubed plus 2x plus 1. So there we've got a partial factorization. And then you could repeat this until you have a total factorization. Let's try to find the zeros of the leftover bit. So this leftover bit I'll underline in blue. Okay. So again, the way to do this would just be to check all possible numbers from Z3. And since 0 and 1 are not zeros of x plus 1, and they're not zeros of f of x, then they cannot be zeros of this blue underlined thing. So that means x equals 2 is our only possible 0. So let's see, if we plug x equals 2 into here, we'll get 2 cubed plus 2 times 2 plus 1. But let's see, 2 cubed is 8, which is equal to 2. 2 times 2 is 4, which is equal to 1. So this really turns into 2 plus 1, which is equal to 4, which is equal to 1. So 2 is not a 0, which means this yellow thing is actually our full factorization, which means this blue underlined polynomial doesn't seem to factor anymore. In other words, it would be something that we'll call in the future an irreducible polynomial. Okay, let's move on. So for our next example, I'd like to recall the following fact from the video, which is like kind of important, and that is if R is an integral domain, then the units in the polynomial ring, R adjoint X, are the same thing as the units in the ground ring R. But if you're outside an integral domain, this does not hold. And we saw this in the video. We found a unit in the polynomial ring that was not in the ground ring. And here we're going to find a couple of more examples. So let's find the inverse of 4x squared plus 2x plus 1 inside of z8x. Okay, so let's maybe see how this will go. So our strategy will be to guess the format of an inverse and then maybe use that to develop a system of equations. So let's look at 4x squared plus 2x plus 1 times ax squared plus bx plus, well, actually, we know that this must be a 1 given that we want this whole thing to be equal to 1 in the end, and that's the only way to get a constant term of 1 there. So that's restricted already. Okay, so now let's do this product to see what we get. So we'll have 4a times x to the fourth. That's our x to the fourth term. And then let's kind of eyeball it to get our x cubed term. So we'll have 4x squared times bx, so that'll be 4b. And then we'll have 2x times ax squared, that'll be plus 2a. That's attached to x cubed. And then what's our x squared term? Well, we'll have 4 plus a. So we'll have, like I said, 4 plus a plus, let's see, 2b. Okay, 2b, like that. That's our x squared term. And then what's our x term? So our x term will be 2 plus b. So we have plus 2 plus b times x. And then finally, we'll have our constant term, which is 1. And like I said, we want that to be equal to 1. But notice that gives us a system of, well, it's not exactly a system of equations, it's a system of congruences. We know that 4a must be equal to 0. We know that 4b plus 2a must be equal to 0. We know that 4 plus a plus 2b must be equal to 0. And finally, we know that b plus 2 must be equal to 0. And the important thing is all of these are equal to 0 inside of z8 because we're inside of z8 adjoint x here. Okay, so now let's see if we can solve this. And I think we can fairly easily using this fact right here that b plus 2 equals 0. So since b plus 2 equals 0 inside of z8, that means b equals negative 2, but negative 2 is equal to 6 inside of z8. But now we can plug that in right here to get what a has to be. So we have 4 plus a plus 2 times 4, which is 12, equals 0. So that's from this equation right here. Okay, but let's notice that 4 plus 12 is equal to 16, but 16 is 0 inside of z8. So in the end, we'll get that a is equal to 0 inside of z8. Oh, but those are the only things that we needed to solve for. So it looks like we have the inverse, and the inverse of 4x squared plus 2x plus 1 is equal to 6x plus 1. And of course, we would need to check that because we only used 2 of these equations. We would have to check that the other 2 of these equations are satisfied. But I think you'll see that the other 2 of these equations are satisfied, making this whole product satisfied. So that's what we have, and I didn't write out the rest of the details, but we talked through what you would need to do. So there, we found an inverse inside of z8 adjoint x, which is not inside of the ground ring z8, showing that you really do need this R to be an integral domain for this result to hold. Okay, let's move on. So one of the things that we proved in the main video was the division algorithm when you have polynomials over a field. So let's do an example of one of those. Although we already did one, let's do like another example. So let's do the division algorithm with 5x to the fourth plus 3x squared plus x plus 6 and 2x squared plus x plus 3. Let's say we're working over the field z7. So we're going to do our standard strategy here. So 2x squared plus x plus 3 is dividing into 5x to the fourth plus 3x squared plus x plus 6. So to achieve this 5, we need to multiply 2 by something to get 5 inside of z7. And I think maybe the appropriate strategy here is just to go through all of the elements of z7 like in your head until you see one. And I think you'll see that 6 works. So we need to multiply by 6x squared. And that's because 6 times 2 is 12, but 12 inside of z7 is 5. So that'll give us, like I said, 5x to the fourth because 5 is equal to 12. And then plus 6x cubed. Good. Okay, so now let's continue going on. So now we'll group and subtract. So the 5's and the 5's cancel and we get negative 6x cubed. But negative 6 is the same thing as positive 1. So that gives us x cubed plus 3x squared plus x plus 6. So notice this like thing that we're dividing into didn't have a cubic term. So now we've got a cubic term. Okay, now we need to determine what do we need to multiply by 2 to get this coefficient of 1? What will be the inverse of 2 inside of z7, which is 4. Because 2 times 4 is 8, which is 1 inside of z7. So here we'll go plus 4x. So 4 times 2 is 8, which is 1, so I'll put an x cubed here. Then 4 times x will be 4x squared. Great. Now let's group and subtract. So the x cubes cancel. We have 3 minus 4, which is negative 1. But inside of z7, negative 1 is the same thing as positive 6. So we have 6x squared plus x plus 6. Now, what do we need to multiply by 2 to achieve 6? Well, that's easy. That is 3. Now 3 times 2 is 6x squared. 3 times x is 3x, so we have plus 3x. Great. Now group and subtract, and we'll see that the 6's cancel. X minus 3x is negative 2x. Negative 2 in z7 is 5, so we have 5x plus 6. And there's our remainder because we got something that has a degree smaller than this right here. Now we could maybe write a conclusion over here that 5x to the fourth plus 3x squared plus x plus 6 is in fact equal to 6x squared plus 4x plus 3 times 2x squared plus x plus 3 plus our remainder, which was 5x plus 6. And there we've done it. We've exhibited the division algorithm in this case. Now let's move on. So for our next example, I'd like to recall a couple of facts that motivate this example. So maybe the first one, although I've written it third, is that R is an integral domain if and only if R adjoin X is an integral domain. We proved that a couple of videos ago. Then we also proved that if P is a prime ideal of R, then P adjoin X is also a prime ideal of R adjoin X. And that hinged off of this fact right here. Well, actually these two facts right here, but maybe this one right here that says R mod I adjoin X is isomorphic to R adjoin X mod I adjoin X. But notice what we do not have here is R as a field implies R adjoin X as a field. And we actually know that is not true. And we'll see that at work in this example. So let's give an example of a maximal ideal M in a ring R such that M adjoin X is not maximal in R adjoin X. Okay, so let's see how this goes. So let's take the ideal 2z inside of z, and let's note that 2z is maximal because z mod 2z is isomorphic to z2, which is a field. Recall that an ideal is maximal if and only if the corresponding quotient ring is a field. Okay, so however, things go wrong if we look at the maybe polynomial version of this. So let's notice that z adjoin x mod 2z adjoin x by this isomorphism over here is isomorphic to z mod 2z adjoin x, which by the fact that z mod 2z is the same thing as 2z, this is isomorphic to z2 adjoin x, I should have said. Great. But now this thing over here is definitely not a field. And how do we know it's not a field? Well, let's notice that x does not have an inverse. In other words, it is not a unit. Great. So now since z2 adjoin x is not a field, that implies that 2z x is not maximal. Because if it were maximal, then this would be a field, but we just showed that it's not a field. Okay, so anyway, this might seem like it's hard to get at an example, but in fact, if you just are comfortable with like our previous results, the example almost jumps out at you immediately. Okay, let's move on. Next up, we're going to look at a really classic proposition. And this has to do with the derivative of a polynomial and the multiplicity of a zero. So let's suppose that f is a field, alpha is an element of that field, and f of x is in the corresponding polynomial ring. Then we can write f of x as x minus alpha squared times g of x if and only if f of alpha and f prime of alpha are 0. And here we're just going to take for granted that all of the normal derivative rules hold, although that'll likely be an exercise if you're in my class. Okay, so let's get to it. So this is an if and only if statement, which means that there are two things to prove. Let's go with this forward direction first. So that means we'll suppose that we have f of x equals x minus alpha squared times g of x. And now let's notice that immediately we see that f of alpha is equal to alpha minus alpha squared times g of alpha, which is equal to 0. So that gives us one part of this equality up here. And now let's take the derivative. So also we see that f prime of x is equal to, using the product rule, 2 times x minus alpha times g of x plus x minus alpha times g prime of x. That should be x minus alpha squared. But notice that immediately tells us that f prime of alpha is equal to 0 because we get an alpha minus alpha here and an alpha minus alpha there. Okay, so now let's go in the reverse direction. Okay, so let's see how that might go. So from a result in the video, we know that if something is a 0 of a polynomial, you can factor it out. So what does that mean? Well, that means that f of x equals x minus alpha times a of x, and f prime of x equals x minus alpha times b of x. That's because alpha is a 0 of f of alpha and f prime of alpha. And now we'll essentially put these two things together. So let's notice that x minus alpha times b of x equals f prime. But then we can take the derivative of f using this version. So let's see, that'll be equal to a of x plus x minus alpha times a prime of x. That's by using the product rule over here. And now we can solve this for a of x. And solving this for a of x, we'll get x minus alpha times b of x minus a prime of x. But now let's set this b of x minus f prime of x equal to g of x. And if we do that and plug this version of alpha up here, and plug this version of a of x up here, we will immediately have the result. Notice this will be equal to x minus alpha squared times g of x. Great, and that's a good place to stop.